hello everyone. So I'm Ramzi Messahel. I'm a research engineer at Safran. And today I will present a work on the recent implementation of a data interpolation library that is portable thanks to Kokkos and ArborX. So for the outline of the presentation, I will start by presenting you the context of this work, maybe who we are, if you don't know who we are. And I will then present the finite-element interpolator, and in particular the motivation for using Kokkos and ArborX for the portability. And I will try to highlight this portability through benchmarks and results on different CPU, GPU architectures. And finally, I will end this talk with a conclusion and some future work on the current project and also on other projects that we want to use Kokkos and ArborX on. So at Safran, who we are? So Safran Group has a mission to design and manufacture high technology systems and also equipments for the aerospace and defense sectors. So if you consider here, for example, an aircraft, civil aircraft, so you have a lot of components that we product. So you have landing gears, sliding evacuation slides, seats, nacelles, and of course the favorite one is the aircraft engine. And to do that, so we have HPC and scientific computing everywhere. So for the design of our products, so we have numerical simulation that is there for the full life cycle, from the early design stage up to the operational stage. So we use numerical simulation in design offices, but also to understand the maintenance and the repair, giving inputs from the users, for the customers, sorry. We also have numerical simulation for the manufacturing process. And we also have HPC and scientific computing for mastering and reduce the development cycles, to master the risks around the manufactured part, and also to master the uncertainties that may come from the environment, the material, or for example, the manufacturing process. And we also use HPC and scientific computing with our AI colleagues, so in order to combine physical numerical models and some recent machine learning approaches in order to design fast and robust decision-making tools. So if we take, for example, this aircraft engine, here you have a couple of problems that we try to solve in our research units. So they are all multi-physics coupled problems. So you have, for example, FSI with burst strike on fan blades. We also have some coupling of Euler and Lagrangian method for the lubrication of gears. We have also some combustion problems, aerothermal stimulation around turbine blade, and so on. And the common point for all this coupled simulation is that they all rely on a data interpolator on a library. But the thing that opposes all of this simulation is that most of them use their own data interpolator. This is mainly driven by the fact that they all evolve in different environment contexts. So some of them rely on some CPU codes, some GPU codes. We also have some codes that run low fidelity simulation, high fidelity. We also have different programming models on the code. So we have Python codes, C++ code, and Fortran. And what we try to bring with this project is to have a library that can be portable in order to run on the CPU code that we have, the GPU codes. So for the on-node level, we try also to add the MPI layer. And we also try to provide to the user some interfaces. So we already have the Python interface, C++ one, and we also have a prototype for the Fortran user that would like to onboard on our library. So now to dive a bit deeper in the numerical methods and where we have the data interpolation. So you have the coupling of different solvers where we need to transfer and interpolate the data between the solver and the interface. We also have a lot of activity in mesh adaptation, where each adaptation of the mesh, you need to transfer the data from one mesh to another one. I already discussed about the Euler-Lagrangian, the particle relocation method. We also have some crack propagation activities and remeshing, where here the difference with mesh adaptations is that we can also have some contacts. And we also have some use cases in the AI community, where the colleagues from AI are using our library to first subsample their data that provides some high fidelity simulation on very fine grids in order to have something that they can use for the training. And we also have some use of data transfer in the inference states, where they use the combination of some morphing methods with graphic neural networks, and that they need to transfer the data every time they morph the mesh and they move the mesh. So regarding the library, so the problem to solve is very simple. In input, you have a finite element mesh, and an output, you have a point of cloud, and what you want to do is you transfer the data from the mesh to the cloud. So we don't make any assumptions, so as we treat many problems for many engineers in different fields, so we had to cover the full stack of finite elements. So we have 1D, 2D, 3D finite elements, line, triangles, quads, up to eggs and pyramids. And we focus on the red little square. So we have two scenarios. So if we are inside the finite element, it's very easy, so we interpolate the data, and that's it. But if we are outside, we have a couple of options. We can either select the closest node value, or we can project the node on the closest element and interpolate on this point, or we can use the closest element to extrapolate. And the main ingredient to do that is to use an iterative inverse mapping. So for each point, what we do is that we will try to find its, the element that includes it into the local frame by using this inverse mapping. So we just move from the global reference frame to the local frame, and this is done solving this nonlinear equation. And this is the main ingredient for our data interpolator. So in the reference frame, it's much more easier to find whether we are inside or outside. And if you are outside, then we have to apply a special treatment. So why Kokkos and ArborX? So we had the first implementation long time ago. It was Python-based, using a KD tree for the spatial indexing. And it was very slow, so there was one first attempt to accelerate it, moving on to C++ and using Boost library. But we were really stuck to and damn slow to the bottleneck of the sequential parts. So when we decided to improve this library, so we thought that first we would need to be in a full multi-threaded environment to leverage this bottleneck. And the other one is, since we had to rewrite the code, it had to be portable in order to be able to run on CPU and GPU. And the combination that matches our need was ArborX and Kokkos, that was responding to these assumptions. The other thing that we've done recently is that we have moved from the linear algebra library to Kokkos Kernels. So why? Because to solve our Newton problem, but for also other application material models, we have a lot of small batch operations. So we have GEM, GEMV, AXPy, but also some math inversion. And most of our codes were very CPU-oriented code. So for the legacy one, so far, again, was very nice and very efficient for many reasons. The first one is that it provides all the storage objects that we needed for our needs, so vectors, matrix, and also tensors. It was very fast on CPU, thanks to lazy evaluation and also some explicit vectorization. And the other thing that we really appreciate a lot is that they had a very nice high-level abstraction that allows you to write some C++ code that was really close to the pen and the paper. Because at the end of the day, what we give is we give interface to some engineers that what they care about is to do some design, implement some material models and so on, and for them that they don't want to struggle with the programming and the coding. But there is a but. So when we try to move to the GPU implementation and portability, what we found out is that there was many functions that were not ported, and in particular the matrix inversions ones. So we just had a crash on runtime. So for QR, LLT, LDLT. So we tried to bring our own implementation, but that wasn't efficient. Another thing that we found out is for some of the function that was already there, so there were some issues with the accuracy. And the last one is also in terms of interoperability. You don't have that easy way of managing your code on runtime, selecting either device or host mode. So everything, it's when you compile with MVCC, for example, everything tends to run on the GPU, and that was also a bottleneck in terms of architecture. So for that reason, so we moved to full Kokkos ecosystem. So with Kokkos and ArborX and the Kokkos Kernels for the linear algebra part. And just the last point about ArborX and the callbacks. So ArborX provides a system of callbacks that allows the user to inject its own function and functionalities while it does the the geometric search intersection. And this is something that we use in particular to handle the mesh heterogeneity. So what we do is that we only seek for the intersection between the query point and the bounding boxes. And when we intersect the bounding box, then we apply our Newton method. So to go back in the reference frame and to check whether we are inside or outside. If we are inside, so that's it, we interpolate. And if you are outside, so we apply another treatment. And for example, if we consider the projection to the nearest element, we also use the same trick. So I didn't display all the code here, but we create the skin of the mesh, so using Kokkos. And then in ArborX, we also seek for the closest triangle after the triangularization. And with the callback, what we do is that when we reach to the closest triangle, we use this projection that is computed by ArborX to get the projected node and to evaluate the interpolation. And that's something that we really appreciated. So in terms of performance, yes, one last thing that I forgot to say is that I didn't find any solution so far. So I have a big branching here because since a priori you don't know what type of finite element you will hit, you will probably hit a tetra, an hex, a pyramid, and so on. I have a big switch that is hidden over there, and I will try to show the impact on the performance. So this is one simple example where we have our industrial turbine blade that is meshed by the design engineer. So this is something that we cannot touch. The mesh is something we don't want to touch, we have to work with. And most of the meshers that try to be X-dominant, and so this is why we have almost 70% of hexa elements. And then afterward, they try to fill the domain with what they can do. So most of the time, we end up with some kind of meshes like this, where we will have all type of finite elements. And what we have done is that we really focus on the GPU implementation, in opposite to what people do, since we had the chance to rewrite from everything. So we didn't focus on CPU then porting. We really focused on the GPU part, and then we activated the OpenMP runtime to see what we'll have. And we were very happy to see that we managed to gain some scalability, and that the code was portable and also scalable. So this is on my laptop. And to check the effect of the branching here, so I compared the results in green on a hybrid mesh and also with a full tetrahedralized mesh. And we saw that we didn't lose that much, so we are very happy. And this is one last test case on a more fine problem. So we have tested also our implementation on different devices. So OpenMP AMD Zen 4 cores, CUDA H200, also HIP. And we also saw that pushing it to 128 cores, so we managed to still get some scalability, and that was pretty fair for, I really appreciate the results, knowing that the target is more to run at the NUMA level or the socket node. So, but it was really nice to see that without changing the code at first try, we managed to get some scalability for OpenMP. And also before the conference, so past week, I have tried it on HIP AMD. It just worked at the first try. This is something that we also really appreciated. Now for the conclusion, so we are really happy with Kokkos, ArborX, and Kokkos Kernels. It really has demonstrated the portability, both in terms of performance, but also in terms of coding. So first try, it worked really nicely on OpenMP and also with HIP on AMD. It has also demonstrated some robustness, because I didn't show here all the use cases, but for our complex industrial cases, it always worked, even with difficult and complex geometries. This is something we really appreciated. And one last part is that we had a need to focus on kernel methods, because we also have data that does not come from numerical simulation with the mesh, but that comes from the experimental parts. And for this type of problem, so we only have a point cloud, so we have implemented a kernel method, and that was done entirely by our intern student, and that did everything by his own. So he was very good, but he was very helped by also Kokkos lectures, by the Slacks also discussion, also with Spack to install all these things, and he was also really helped with Kokkos tools and HPC toolkit for the optimization process. This is something we wanted to share with you. And finally, for the future work, so I wasn't able to open source the library for the conference, but it will arrive very soon. So at Safran in the research department, so we try to push all our codes open source. So here you have a link to our GitLab repo, and very soon you will see also this library. And that was the first warm-up. It was the first really project that we pushed from start to end, and that we continue to work on with the Kokkos and the ArborX. And now we want to go a bit further in much more bigger applications, just to cite two of them. So we have here the generation of polycrystalline turbine plates, where we have these crystals that are designed on some simple X meshes, and then we will project into the intersection with the final product to have this final blade. And we also working on some contact prototypes that work very well in terms of scalability. Here you have the scalability for hybrid runs and for GPU. And we will try now to push it in production in our internal codes. And yeah, and I wanted to thank everybody. So the TGCC for the computational resources, the Idris Hackathon and NVIDIA because they started in a hackathon, and also the HPSF Foundation for all the nice tools that really help us to do very nice things. Thank you so much.
Thank you. Questions? No one gets to go to lunch without questions.
Mine is not really a question, it's a comment. The meshless interpolation that you mentioned, ArborX actually has a package to this. You might want to compare. We also had
yes.
developed this.
Yes, we have a plan. This is a recent inter project, and we had a demand to use this method actually, but we also pushing for the MLS inside our library to have a wrapper to it.
Okay.
Yes.
Excellent.
Yeah, this was really great to see. So one question I always have is like, what do we need to do in order to make, the use of our products more viable in like actual industrial commercial settings? Is there things you can think of, other than, showing that it actually works and it actually does what we say it does, right? What you would need from us, are there non-technical barriers,
yes.
Which would prevent
yes.
use in actual production environments?
Yes, so one that I have, because I jumped in a new project that focuses on Fortran legacy code, it's interoperability. So we also, when I mentioned all the different applications, we also have many legacy codes. And what we're trying to help people to do is to be able to have more interoperability with different languages. And this is something that we are looking into, and hopefully tomorrow I'll find a couple answers to my question. But interoperability with Fortran, this is a big one because we have many legacy codes that have been running for 20 years that we are still running in production.
Thank you, Randy. Can you come back to the batch kernel slide?
Yes.
You said that in the iGen does not support some linear solvers like QR and LT, DLT, and are they available in Kokkos kernels? I'm not sure.
For the QR, yes, because this is what my student used. For the other ones, I'm not pretty sure.
Okay.
Because for this project, I didn't use it. He used it for the kernel methods.
Yeah.
But for the QR, he definitely used it because he had some issue due to the conditioning of the matrices and so on.
So if it is not available, you implement it by your side, or you are using different method?
For the QR method, no, it was there. Correct me if I'm wrong. But for the other ones, so it's already implemented from the CPU side, but it didn't have the decoration to use it on heap, or because this is how it works on Eigen. So, and since it was a project that hasn't released for so long, so we didn't want to work on it and to work on something that has a more frequent releases and in terms of sustainability.
Thank you.
Thank you.
Cool.